Okay, students, let's begin lecture. This is our last lecture of the semester. We're going to do a little wrap-up commentary of what we've been doing. Then we'll do a semester a bonus points review, which I mentioned last week. I also have some of the homework X submissions graded, and I'll be calling those people up while you guys are clicking. So. What time is our final exam? On what day? Friday? Okay, good. All right. You may recall the very first day of lecture. We did some observations. We looked at skateboarders and we looked at bicycle wheels and stuff. The turntable, the angular momentum. And we looked at the spectral fingerprints of hydrogen, and I told you a little bit about that kind of situation. And you might ask yourself, why are they so important? And the answer is, we wanted to introduce skateboard interaction concepts, angular momentum concepts, energy, and all that other stuff, so that we could eventually study eventually have tools to study and understand hydrogen. And we almost have all the tools now. And when we talk about understanding hydrogen, it might be, some star-forming region that we look at through a telescope, like the Rosette Nebula here. This is a star-forming region way out in the universe. And that beautiful red color that you see there is hydrogen gas. And the red H alpha light from that is its signature. That's how we know it is hydrogen. When you see all those little stars and they're forming, and they're deforming the cloud, they're making bubbles in it and stuff like that because of their solar wind. Another quantum system that you can think about as being a worthy objective, from simple hydrogen to something very complicated, the retinal molecule. Now, here are the two forms of retinal that exist in your eye at any given time. A photon of light will turn an 11 cis retinal into a all trans retinal, and then it'll buckle back down into the 11 cis configuration. That's the lower energy state. And all of that is a result of electrostatic potential energy. And that is what you will learn in Physics 2054, probably in the first few weeks. All right? So you have all the tools now to tackle electrostatic potential energy and electrostatic potential, which is different. That's what we call voltage. It's not exactly the same as potential energy, but it is related to it. And why is that important? To understand the quantum theory of hydrogen, the fact that you have countable energy levels and no others, and that when the electron drops from n equals 3 down to n equals 2, it emits a red photon of light, the H alpha photon, a very specific color. That all comes from understanding the energy, the electrostatic potential energy of a simple hydrogen atom, which is a proton and an electron, very simple to model. And we've modeled it successfully. The photon that goes out has a specific energy related to its color, wavelength, and frequency, which we've talked about a little bit in terms of waves and stuff. Now, this particular quantum theory of hydrogen is about 100 years old, where you have these very precise, almost like planetary orbits. Now, we don't think that that's the case anymore. What we think now is that these orbits, that we still think of orbital states, but we don't think of little planets. We don't think of the electron as being a little planet. We think of it as being a wave. And if an electron can be understood as a wave, aha, nice, you saved the day. Nice. I left all our, huh? What?
I'm just kidding.
Dude, don't do that. Good, thanks. The exact worst thing to possibly do. He went over to my office to get our review sheet. So anyway, so this whole idea, why is it that an electron can only operate at certain altitudes above the proton? Nobody figured that out until about 1925, around in there, when a guy named de Broglie said, well, treat it as if it's a wave. And then, if it's a wave, it will constructively interfere with itself if the wavelength is equal to one orbit or half an orbit or a third of an orbit. So you get three waves, one wave per orbit, two waves per orbit, three waves per orbit. And the fact is, his conjecture, de Broglie's conjecture, was right, and we now see that. We can send electrons into, like, this is a picture of some randomly oriented no, this is aluminum crystals, an aluminum foil actually. So it's a metallic foil. And we can send X-rays through, and that's a form of electromagnetic radiation waves, and they diffract. That's the picture on the right. And when we send electrons through, they do the same thing, except they're not at the same energy as X-rays, but they still form these ring-shaped patterns. Now, what we saw on the first day of class was lines, vertical lines to the left and to the right. Do you remember that? And that's because the diffraction grating was a set of parallel lines photocopied onto that piece of clear plastic. This thing is going through randomly oriented. So it's like zillions of different lines, all the same size apart, or actually different sizes apart, producing this kind of ring-shaped pattern. But that's the electrons behaving as a wave is something that we can understand. So all this stuff that we're heading for, or that we've finished heading for, we've got almost all the tools in place, will allow you to understand all of chemistry from a physics basis. And here's the last part that's pretty cool. We've put in place the whole idea of a phase space configuration for an oscillating and other systems, like the fibrillating systems, the heart. And what we find is in the atom that those quantum leaps from like n equals 3 down to n equals 2 for hydrogen, that gives you the H alpha photon. That corresponds to jumping ellipses from one energy state down to the next, kind of like on homework X. And now you know why I was thinking ellipses with homework X. And here's the cool part. If you say that an electron is a wave that constructively interferes with itself, it can only exist in certain orbits. The wavelengths won't be right to have constructive interference at any altitude, only certain orbits. And guess what? When you do the phase space reconstruction of them, the differences, the jumps in phase space are in units of Planck's constant, h. So multiples of h, 2h, 3h. So if you jump down from n equals 3 to n equals 2, you've jumped down in phase space by a factor of h. That's Planck's constant. And it is for this reason that I always think of Planck's constant as the one constant to rule them all. It is in every physical reaction, because all of our dynamics in this universe in which we live are mediated by quantum transitions of that kind. And so that is what we've been chasing all semester. And next semester in 2054, or whatever it is you get to 2054, you'll be putting it all in place, and you'll be able to really understand why Max Planck and his constant, the one constant to rule them all, is such a profound result, and actually it's a profound mystery in this physical world that we live in. Okay, that's the wrap. And what we're going to do now is we're going to take the last 36 minutes to do a in-class review. It's going to be for bonus points, as I've mentioned. And the directions are on the top of the page, first page. And I'll get the clicker set up here, and you can start circling answers. It's mostly multiple choice. Santi, here, let me take the answer key out here. Just give this to, yo, what is your name? Chris. Give this to Chris. Chris, hand him out upwards and to the left and to the right. Just stay in your seat. Stay in your seat. Just hand him back. Okay. Okay, white hat in the first row. What is your name again? Peyton. Okay, give this pile to Peyton. Just hand him, just stay where you are. Just start handing them upwards. Come on, hand them upwards. Get those piles moving up. Uphill. You don't need that many for your, don't count them out, just take them. Move them up. Send them uphill. Diffuse. We're doing diffusion here. Take a pile and take some for your row and send them up. There we go. Right now, you may work with your neighbors. Work carefully and quickly, and that will be good.